For over half a century, astronomers have been haunted by one question above all others. It isn't about whether planets exist across the galaxy, but whether they exist right next door. Alpha Centauri, the nearest sun-like star system to Earth, has always seemed like the universe's ultimate tease. It is close enough to dream of visiting and similar enough to feel familiar, yet remains stubbornly silent. Every effort to find planets there has failed. The stars were too luminous, the system too volatile, and the technology never quite up to the task. Then the James Webb Space Telescope did something it was never designed to do. It aimed its most sensitive instruments at one of the brightest stellar systems in the sky, pushing itself far beyond its intended limits. What saw did not offer clarity. It offered unease. A planet appeared next to Alpha Centauri A, and then it vanished. It was a detection strong enough to survive every statistical test, followed by a silence where certainty should have been. It revealed orbital paths that shouldn't exist. It presented conditions that challenge how planets form, how they survive, and how close potentially habitable environments might actually be to Earth. This story isn't just about a single observation. It is about proximity becoming a problem rather than an advantage. It is about technology being forced out of its comfort zone, a planet that refuses to act like a planet, and the uncomfortable realization that our nearest stellar neighbor might be far stranger than we ever feared. What James Webb saw in Alpha Centauri didn't answer our oldest question. It made it more unsettling than ever. When James Webb observed Alpha Centauri A in August 2024, astronomers weren't expecting a clean result. The target itself broke almost every rule of exoplanet hunting. The star's brightness overwhelmed the detectors. Its binary companion flooded the field with contamination, and its rapid movement across the sky made precise pointing a nightmare. And yet, after hours of observation and months of custom data processing, something emerged from the glare. A faint point of light appeared roughly 2 astronomical units from the star. It wasn't marginal. It wasn't ambiguous. The signal hit a statistical significance of 5.5 sigma, strong enough that random noise was essentially ruled out. Against all expectations, a planetary candidate had revealed itself beside the closest sun-like star to Earth. The team didn't celebrate. They interrogated the detection. They tested and retested every known source of error. Background stars were eliminated using Gaia catalogs. Distant galaxies were ruled out through spectral behavior. Moving solar system objects were excluded by tracking motion during the observation itself. Instrumental artifacts were challenged through injection and recovery tests designed to expose false positives. The signal survived all of it. Split data analysis showed the object appearing consistently across independent subsets of the same observation. Whatever S1 was, it behaved like a real astrophysical object bound to Alpha Centauri A. For the first time, the concept of a planet around our nearest solar twin moved from speculation to measurable evidence. Confirmation should have been straightforward. Planets move. Their positions shift predictably over time. Follow-up observations were scheduled for February and April 2025, using the same techniques that revealed S1 in the first place. The telescope performed flawlessly. The data were processed with the same pipelines, the same reference stars, and the same corrections. And yet, the planet was gone. The region where S1 had appeared clearly in August showed nothing but noise. No trace, no marginal signal, just absence. A planet that passed every test had apparently disappeared. The results stunned the team, not because it contradicted expectations, but because planets don't behave this way. Gravity does not permit objects to simply vanish. 3 explanations remained. The first was deeply uncomfortable, an extraordinarily rare statistical fluke. The second involved an unknown background source that somehow evaded every catalog and test. The third was the most unsettling and the most intriguing. S1 could be real, but moving along an eccentric, inclined orbit that carried it into regions where JWST's coronagraph becomes effectively blind. Orbital simulations showed that more than half of all stable orbits consistent with the August detection would naturally result in non-detections during both February and April. In other words, the disappearance didn't disprove existence. It fit. The planet didn't vanish. It moved into the dark. Alpha Centauri has always held a special place in astronomy, not because it is exotic or distant, but because it is familiar and close. At just 4.37 light-years away, it is the nearest star system to the Sun. And Alpha Centauri A, in particular, is almost a mirror of our own star in terms of mass, temperature, and age. For decades, astronomers assumed that if planets were common anywhere, they would surely be found here. This proximity created confidence, even optimism. Unlike distant exoplanet systems that push instruments to the breaking point, Alpha Centauri felt approachable, almost cooperative. Yet, year after year, searches came up empty. Radial velocity measurements failed to find clear signals. Transit searches found nothing reliable. Each null result quietly chipped away at the assumption that closeness makes discovery easy, transforming Alpha Centauri from a promising target into an unresolved problem. The document makes clear why Alpha Centauri has resisted detection for so long. Its very brightness, the quality that makes it visible to the naked eye, becomes a liability for precision instruments. The star overwhelms detectors, saturates sensors, and floods the field with scattered light. On top of that, Alpha Centauri is not alone. Alpha Centauri A and B orbit each other in a tight binary system, constantly shifting positions and contaminating observations with overlapping glare. The star's rapid proper motion across the sky further complicates long-term monitoring. Instead of a stable target, astronomers are dealing with a moving, blinding, gravitationally complex system. The closer they look, the more the star fights back, turning proximity into a technical obstacle rather than an advantage. As technology improved, and still no planets were confirmed, a deeper doubt began to form. Some researchers started to ask whether Alpha Centauri simply never formed planets at all. The gravitational influence of its companion could have disrupted planet formation early on, stripping material from the disk or preventing stable orbits from ever settling. Others proposed that planets might exist, but only on extreme orbits, tilted, eccentric, or dynamically unstable, making them nearly invisible to traditional detection methods. The absence of evidence began to feel meaningful. Alpha Centauri transformed from a promising neighbor into an unsettling outlier, a system that challenged the assumption that sun-like stars naturally produce planetary systems like our own. What the document emphasizes is that James Webb didn't just observe Alpha Centauri with better sensitivity. It approached the system differently. By using mid-infrared wavelengths and advanced coronagraphy, Webb bypassed many of the limitations that crippled earlier searches. The detection of S1 didn't merely suggest the presence of a planet. It shattered the idea that Alpha Centauri was empty. It showed that planets could exist there, but not in the neat, cooperative configurations astronomers hoped for. Instead, if S1 is real, it implies a planetary architecture that hides itself, evades confirmation, and punishes assumptions. Alpha Centauri was never simple. It only looked that way from a distance. Webb's glimpse revealed a system that resists easy answers, even when it is closer than almost anything else in the galaxy. From the moment the S1 candidate was detected, its proposed position around Alpha Centauri, it triggered immediate concern among dynamicists. The object appeared at a projected distance of roughly 2 astronomical units from the star, a region that sits uncomfortably close to the gravitational influence of Alpha Centauri b. In a binary system like this, gravity does not behave politely. The companion star repeatedly disturbs planetary orbits, injecting energy, altering trajectories, and often ejecting planets entirely over long timescales. Existing models predict that stable, long-lived orbits in this region should be rare or non-existent unless very specific conditions are met. Yet, S1 appeared exactly where theory says planets should struggle to survive. This wasn't a small discrepancy. It was a direct confrontation between observation and the mathematical frameworks astronomers use to decide what is even possible. The document explains that the only way S1 can exist without being torn apart or ejected is if it occupies a highly unusual orbit. Simulations show that stable configurations are possible, but only when the planet follows an eccentric path, spending much of its time far from the star before briefly diving inward, or when its orbit is significantly tilted relative to the plane of the binary system. These orbits aren't neat circles. They are stretched, angled, and dynamically complex. Crucially, such orbits would naturally cause the planet to disappear from view for long periods, especially when observed with coronagraphic techniques that are blind near the star. In other words, the very same orbital properties that make S1 difficult to confirm are also the properties that allow it to survive at all. Stability, in this case, comes disguised as invisibility. Surviving in such an orbit is one challenge. Forming there is another entirely. The document highlights that planet formation models struggle even more than stability models when applied to Alpha Centauri A. In the early stages of the system, the gravitational influence of the companion star would have stirred the protoplanetary disk violently, increasing collision speeds between dust grains and preventing them from sticking together. This environment is hostile to the slow, orderly growth that planet formation requires. If S1 exists, it either formed much closer to the star and migrated outward into its current orbit, or it formed under conditions that current models do not account for. Both possibilities are problematic. Migration pathways in binary systems are poorly understood, and alternative formation scenarios remain speculative. S1 doesn't just challenge where planets can exist. It challenges how they come into being at all. What makes this theme especially unsettling is that the models being challenged are not fringe ideas. They are the same frameworks that successfully explain thousands of other planetary systems. Alpha Centauri forces those models into a corner. If S1 is real, then either our understanding of planet formation in binary systems is incomplete, or the stability criteria we trust are missing critical variables. The document doesn't claim a solution. Instead, it exposes a gap, a place where observation has moved ahead of explanation. S1 becomes more than a planet candidate. It becomes a test case, a stress fracture in planetary theory, suggesting that nature may routinely find ways to build and preserve worlds in environments we have long considered too chaotic. The fear isn't that S1 breaks the rules. The fear is that the rules were never complete. The James Webb Space Telescope was never designed to observe stars like Alpha Centauri. Its instruments were optimized for faint, distant objects, for galaxies barely visible at the edge of cosmic time, not for one of the brightest stellar systems in the sky. Pointing Webb toward Alpha Centauri was already a technical gamble. The star's overwhelming brightness risked saturating detectors, flooding the field with stray light, and producing artifacts that could easily masquerade as false signals. According to the document, the decision to attempt this observation wasn't routine. It required deliberate planning, custom observing modes, and the acceptance that the telescope would be operating outside the comfort zone envisioned by its original designers. This wasn't Webb doing what it does best. This was Webb being pushed to do what it was never supposed to do. The breakthrough came through the use of Webb's mid-infrared instrument, MIRI, combined with coronagraphy. Even then, the challenges were extreme. Alpha Centauri's brightness created a complex pattern of diffraction spikes, thermal noise, and scattered light that overwhelmed standard processing techniques. The document details how the research team had to build a bespoke data reduction pipeline, carefully modeling the star's glare and subtracting it piece by piece. Reference stars were used to calibrate the system, but even tiny mismatches in brightness or spectral type could introduce misleading residuals. Every step carried the risk of either erasing a real signal or creating an artificial one. What makes the S1 detection so unsettling is that it survived this hostile environment. Against one of the brightest backgrounds Webb has ever faced, a coherent point source still emerged. The document emphasizes a critical and uncomfortable truth. Webb's non-detections and later observations do not necessarily mean absence. Coronagraphs are blind in specific regions close to a star, and those blind spots shift depending on wavelength, orientation, and observing geometry. In February and April, S1's predicted position placed it closer to regions where MIRI's sensitivity drops sharply. This means that Webb, despite its power, may simply not be able to see the planet at certain orbital phases. The telescope becomes the limiting factor, not the object itself. This introduces a deeply unsettling possibility. The planet could exist, move exactly as physics predicts, and still evade detection purely because of how Webb's optics interact with an extremely bright star. Confirmation is no longer just about more data. It is about whether our instruments are capable of seeing what is actually there. What this theme ultimately reveals is that the Alpha Centauri observations represent more than a single planet hunt. They mark a shift in how astronomers are willing to use James Webb. By pushing the telescope beyond its original specifications, the team demonstrated that nearby bright stars aren't completely off-limits, only extraordinarily difficult. This opens the door to future observations of other challenging systems, but it also raises the stakes. Discoveries made in this regime will always carry uncertainty, ambiguity, and controversy. The document makes clear that S1 exists at the edge of Webb's capabilities, where detections are possible, but confirmation is fragile. James Webb didn't simply observe Alpha Centauri. It revealed where the boundary between what we can see and what remains hidden truly lies. And that boundary is far closer to us than we would like to believe. The document makes it clear that the importance of S1 doesn't come from the planet itself, but from what its existence implies. If S1 is real, it is most likely a gas giant, not a rocky Earth-like world. At first glance, that might seem disappointing, but in planetary science, gas giants are not dead ends. They are gateways. A massive planet carries gravity, structure, and long-term stability. And wherever a gas giant exists, the possibility of moons immediately follows. In our own solar system, the most promising environments for life aren't planets, but moons like Europa and Enceladus. The existence of S1 around Alpha Centauri instantly raises the possibility of a similar system of satellites. Worlds that could orbit quietly within a giant planet's gravitational embrace, shielded from some of the chaos of the binary star system. One detection suddenly multiplies into an entire unseen architecture. The document carefully explains that S1's proposed orbit places it near or within the habitable zone of Alpha Centauri A, depending on its exact eccentricity and inclination. For a gas giant, this doesn't mean surface habitability, but it dramatically increases the relevance of any moons it may host. A large moon with sufficient mass could retain an atmosphere, sustain liquid water, and experience tidal heating that keeps its interior active over geological timescales. The proximity of Alpha Centauri A, a star remarkably similar to the Sun, further strengthens this implication. Radiation levels, stellar lifespan, and energy output are all compatible with long-term stability. The fear hinted at is not about immediate danger. It is about closeness. If potentially habitable environments exist just 4 light-years away, then the universe isn't distant and abstract. It is uncomfortably near. What separates Alpha Centauri from every other exoplanet system discussed in astronomy isn't just proximity, but feasibility. The document highlights that Alpha Centauri has long been considered the first realistic target for interstellar exploration within human timescales. Concepts like laser-driven sails and relativistic probes exist precisely because this system is close enough to imagine reaching. If S1 exists, and if it hosts moons, Alpha Centauri transforms from a theoretical destination into a concrete objective. Exploration shifts from asking, "Is it possible?" to asking, "What exactly would we go to see?" The mystery of S1 turns Alpha Centauri into a place with coordinates, dynamics, and potential targets, not just a dot on a star chart. The psychological distance between Earth and the rest of the galaxy shrinks dramatically. This is where the document delivers its most uncomfortable implication. James Webb did not confirm life. It did not confirm habitability. What it confirmed is proximity combined with uncertainty. A planet that may exist, may host moons, may reside in a region compatible with liquid water, orbiting the closest sun-like star to Earth, and yet remains just beyond our ability to see clearly. The fear isn't that something is out there. The fear is that something could be out there, close enough to matter, close enough to reach, and close enough to challenge the idea that Earth is unique in its immediate cosmic neighborhood. Alpha Centauri was supposed to be quiet, empty, and reassuring. Instead, Webb revealed a system that hides its secrets well, forcing us to accept that our nearest stellar neighbor may already be far more complex and far more interesting than we ever wanted it to be. James Webb didn't give us certainty. It gave us proximity wrapped in doubt. A planet that appears and disappears. A star system that should have been simple, yet refuses to behave that way. Orbits that challenge theory. Instruments pushed beyond their limits. And a neighbor star that suddenly feels less like a distant point of light and more like a place with secrets, structure, and possibility. What this mission truly confirmed is not the existence of S1, but the collapse of comfort. Alpha Centauri was supposed to reassure us. The closest sun-like star, clean, stable, predictable, empty. Instead, Webb showed us ambiguity, complexity, and hidden architecture. It showed us that even our nearest cosmic neighbor does not follow the rules we rely on to feel safe in our understanding of the universe. The fear isn't that something dangerous is out there. The fear is that something important might be there, close enough to matter, close enough to reach, close enough to force us to confront the idea that Earth may not be as alone in its neighborhood as we once believed. James Webb didn't answer the oldest question humanity has ever asked. It made it sharper, more precise, and more uncomfortable. Because when the mystery is on the other side of the galaxy, it feels abstract. When it is 4 light years away, it feels personal. And that is what we all feared. I'd love to hear what you think about this, so drop a comment below. If you enjoyed our conversation today, please share this video and subscribe to help the channel grow. Every bit of support counts.